So in the last video, what we talked about was comparing pKa's to pH's and using that to determine whether or not particular functional groups were protonated or deprotonated in their acid form, in their base form, so on and so forth. So I thought it would be helpful to go through a particular example. So I know we haven't gone over amino acids just yet, but I've been talking about them a lot, and I figured that using an example of an amino acid would be very, very useful. So what I'm going to do here is I'm going to draw aspartate, which is an acidic amino acid, and I'm going to draw it like this. Okay. Now what I'm drawing here is called the Fischer projection. Okay. An amino acid is going to have this carboxyl group, a hydrogen, and this chiral carbon. If you recall back in the day, chiral carbons have 4 different substituents. This will be the amino group, right? And right here is going to be the side chain. For aspartate, its side chain looks like this. It has a CH2 group and then a carboxylic acid group. Okay, so this is specifically a Fischer projection of L-aspartate. Okay, now I'm going to talk about why the difference between L and D and that sort of stuff, and I'll go into details about amino acids later. Don't sweat it too much right now. But this is L-aspartate, and specifically it's the Fischer projection. Okay. Again, don't sweat that too much right now. That's not the focus of this video. So what I wanted to mention is that this aspartate that I've drawn here has 3 functional groups that we are going to consider important. I'm going to label them A, B, and C. Okay, this right here. So A, B, and C, they're all ionizable groups. Ionizable functional groups. What on earth does that mean? That simply means they can become ions. Okay? Now, if you know in organic chemistry, right, this is a carboxylic acid group, as is this, right? This here is an amino group. Now, we all know that carboxylic acid groups are acidic groups, and amino groups, you should recall, are basic groups, right? And again, the definition comes into play. Acidic side chains, or acidic functional groups, right? They are proton donors, right, generally speaking, and basic side chains, or basic functional groups are going to be good at accepting protons. Okay, so what I kind of wanted to show you right here now is the following. Let me actually draw this out for you. So if this is an acidic group, we can depict this as R and a carboxyl group. So the R just represents some carbon chain, right? So it's the same thing here. They're both carboxylic groups, carboxylic acid groups. So if this is an acid, then its acid dissociation equation will look like this. So if this is an acid and this is its proton, it's going to donate a proton, correct? Because it's an acid. And what will be left is RCOO minus. Okay, so what's going on here? This is the acid. This is the conjugate base. Okay, now, so we drew it out like that because here, A and C, right, these 2 carboxylic acid groups are in their acidic form, right? They're protonated. So they're going to act as acids. I mean, if they are going to act like acids, this is how they would do it, right? But with this here, this amino group is not protonated, right? So it's a basic group. It can accept the proton, right? So what I'm going to do is I'm going to draw that out like this, right? If we have an amino group, right, some R and H2, okay, and it picks up a proton, it'll go and become RNH3 plus, right? It's a plus charge there. Let's circle this minus here. Okay, so now This is its acid form. This is the acid form. This is the base form. So you probably understand why I drew it like this now. Is that I wanted the acids. I wanted these to be written as acid dissociation equations. So this thing has a particular pKa, and this thing has a particular pKa. These are both acids, and these are both the conjugate bases, right? These are protonated, right? They carry the proton. These are deprotonated. They've lost their proton. So, what I wanted to do, like I said, I wanted to do a particular practice problem involving these. But before I do that, I want to just label these really quickly. Right? These are both acids. These are the conjugate bases. Right? So now what's going to happen is, right, is if these groups, right, they're all going to have pKa's, right? Because they can all be protonated, right? So they can all exist in an acid form, but some are going to be stronger acids than others, some are going to be weaker. So those that are stronger are going to be more willing to donate their protons and exist in the base form, and those that are they're not as good as acids, they're going to exist in their acid form, right? They're not going to donate their proton. So what I wanted to do was, like I said, a quick practice problem. Okay, so let's say they tell you the pKa of the side chain carboxyl group of aspartate, which I will abbreviate it as ASP. You'll learn all those abbreviations in a later video. ASP, the pKa of the side chain carboxyl group of ASP or aspartate is approximately 4.0. Okay. At a pH of 5, let's label this as A, part A, what form will predominate? Oops. Predominate. Base or acid? Right now, so base or acid, charged or uncharged. This might not make sense just yet, but it will in just a moment, hopefully. Oh goodness. Let me fix that. Not unchanged. Charged or uncharged. Okay. And the second part of this question will be, oops, that looks like a 13. Let's make that a B. Okay, the second part will be what percent will be in acid form and what percent will be in base form. And in base form. Alright, so how do we do this? Well, we're going to use the Henderson Hasselbalch equation, right? So let's get our green going, right? So we can start doing these using the Henderson Hasselbalch equation. Just to recall. Oh goodness, of course, I just said green and I write in white. Okay, so recall the Henderson Hasselbalch equation is the pH is equal to the pKa plus the log of the concentration of the base over the concentration of the acid, right? So now, in our case, right, if we're talking about, this is asking about the side chain carboxyl group, right? And they're saying that the pKa of it is 4.0, right? So, or approximately. So the side chain of this, or excuse me, this carboxyl group here, this is the side chain carboxyl group. This is called the alpha carboxyl group. And again, I'll go into details about that in a later video. This here, they're saying that the pKa of this this acid group is 4. Okay, they're asking at a pH of 5, what form will predominate? So base or acid, charged or uncharged. This charged or uncharged thing kind of doesn't make sense right just yet, maybe, or maybe it does. Who knows? But if they're asking about base or acid, that means they want us to find this ratio, right? They give us these two values. We need to find this. So let's go ahead and do that. Let's solve for it. So if we want to get this ratio by itself, let's just rearrange this equation. Say pH minus pKa equals the log of the concentration of the base over the concentration of the acid. And then, oops, yeah, that's correct, sorry. And we want to get just the ratio, so we have to undo that log. So we're going to take the base 10. Let me change the color to make that a little bit clearer. So we have to take the base 10 of this entire thing, the pH minus the pKa, the base 10 of that log, to undo that. Okay, and then what we're left with is the base to acid ratio. The base to acid ratio will be equal to 10 to the pH minus pKa. Okay, so now all we need to do is plug in these values. So the base to acid ratio will equal 10 to the pH, which is 5, and our pKa is 4, so 10 to the 1, right? So that means, and 10 to the 1 is 10, right? So what does that mean? I don't want to write it just as 10, right? Although the base to acid ratio is 10, it's not just 10, right? It's 10 to 1. For every one species, every one every species existing in the base form, right? For every 10 of them, there's going to be one in the acid form. Conversely, right? If for every one existing in the acid form, there's going to be one in the or 10 in the base form. So what does that mean, right? What are we talking about? Well, this group, right? This is a carboxyl group, so its acid dissociation equation looks like this, right? So what's the base and what's the acid? Well, in our case, this is the conjugate base and this is the conjugate acid. So we know then that there's going to be 10 looking like this for every one that looks like this, protonated. I hope that makes sense. That means at a pH of 5, we would expect to see more in the base form than we would in the acid form, right? Because there's 10 in the base form for every one in the acid form. So the answer to part A, right, the first part of part A, this base or acid, the base form predominates, right? So let's write that in red since it's our answer. Okay, so base form predominates. Right? Now it also asks the charged or uncharged, which form predominates? Well, the base form predominates, right? Is that charged or uncharged? Well, it's carrying that negative charge there, right? This protonated group is uncharged, right? So the base form predominates, right? And the charged form predominates, right? Now, it's not always the case that the base form is charged. For instance, in the case of an amino group, right, if you look up here, the acid form is protonated, right, and carries that positive charge, whereas the base form does not, right? So bear that in mind when doing problems involving amino groups versus carboxyl groups, okay? So this part B here says what percentage will be in the acid form and what percentage will be in the base form, okay? So, well, we know that there's, hang on just a second, let me note all this was basically the our work for the part A. So now let's do part B. So for part B, we want to know what percentage will be in the acid form, what percentage will be in the base form. Now this can get a little bit tricky. Let's just think about this for a second. The percentage just basically means for every 100, right? So we want to know about parts of a whole. Well, our ratio here tells us we have 10 base for every 1 acid, right? So that means a total, if we just consider this, right? This total, we have 11 things, 11 parts, right? 10 of which are base, 1 of which is an acid. So if we think about that, if we want to find the percentage that will be in the acid form, what we would do is we would take the number of acids. Oops, let's do this in green, sorry. Right, what we'll do is we'll take the number of acid. So actually, before I write that, the percent in the acid form will equal the number in the acid form, right, over the total number of species, right, which will be equal to the number of number in the acid form plus the number in the base form, right? And then we'll have that fraction. All we have to do is multiply that by 100%. So if we do that, then we have the number in the acid form will be 1. Number in the acid form here is 1. Number in the base form is 10. So we have 1. Oops. Goodness gracious. Forgot to write the times 100%. I always forget that. Okay, so times 100% here. Right? So that's going to be 1 over 11 times 100%. And we'll get 9.1%. Right? So that's for the acid, right? So if we want to find in the base form, all we have to do is take this number. Oh, it's a terrible box. If there are some in the acid form and there are some in the base form, here we're saying that 9.1% are in the acid form. Well, the rest have to be in the base form, right? So the percent in the base form will be equal to 100 minus 9.1%, which will be 90.9%. Right? Or you could just set it up the same way we did it here, except instead of putting the number of acids on top, you would put the number of base. The bottom would still be the total, right? And I'll note that here, right? Here is the total, right? Okay. So that's essentially it. In the future, what we'll be doing is you'll be shown a particular, or you'll be asked about a particular amino acid, and you'll be given the pKa of all 3 functional groups. If there's 3, there might be 2. And you'll be expected to draw the amino acid at a particular pH given its pKa's. So I hope that video was helpful, and yeah, I hope that video was helpful. See you next time. Oops.